Okay, this video is going to look closely at Newton's laws. And I'm going to, in the first instance, look closely at them in terms of forces. So I'll start with the concept of forces, and then I'll move on to the concept of momentum. Because in actual fact, though we're obviously Newton's very famed for looking at forces, all of his ideas started originally with the sense of momentum. But let's go over the ideas we know first. Okay, I'm going to talk about Newton's first law. Newton 1. Now this is in the absence of a resultant force. So it doesn't mean in the absence of a force, but in the absence of a resultant force. Let me show you a diagram and describe this. Let's imagine I've got somebody standing on Earth there, and we definitely know that there's weight associated with them, and we also know that there is a reaction force on their feet. Let's call it R for reaction. Reaction 1 and reaction 2, one on each feet. In this situation, what's the resultant force, Fr? Well, it's going to be the weight minus R1 minus R2. Now that looks really algebraic, but what I'm trying to show you is that actually they add up to be 0. I have a weight acting down, and I have two reaction forces acting up, which cancel each other out. And therefore, this situation is a Newton 1. And what's happening to this person? Well, effectively, they are stationary. They don't move at all. Okay, now that's not just the only instance of where forces are balanced. There's another specific one, which we're going to look at next. And that is when a car is travelling along. Here's my bad car. I should have probably got a picture of this. And the engine is obviously generating a thrust. And there is some drag associated and some friction. Drag from the air and friction from the tyres. And this thing is going at 70 mph. Oops. 70 miles per hour. Let me rewrite that properly. So it's travelling at 70 miles per hour. So now, what's the resultant force here? Well, the resultant force is going to be the thrust minus the drag and minus the friction. And that comes out to be 0 as well. I could line up the arrows again, but it's travelling on at 70 miles per hour. The resultant force is going to be 0. So in this instance, we can say that there is no resultant force. In the absence of resultant force, we have the object moving at a constant velocity. And remember, that means both speed and direction. It is both of them. So, how can we then sum up what Newton's first law is? Let me go back here. We can say to ourselves that Newton 1 says a body will remain at rest or travel at a constant velocity unless a resultant force acts on the body. Which I think makes good sense. So the essential parts to Newton's first law are something is at rest or at a constant velocity if the resultant force is 0. Try and remember those terms because they're really useful and they really sum up exactly how Newton 1 behaves. Let's just try and think of a last example, and I'm just going to shrink all of that down. We'll try and sum up those two ideas. Remember, there are two ideas here in one example. Let's take an aeroplane flying. So, a bad drawing of an aeroplane. And let's say we know that it has a weight. We know that there's an associated lift from the wings. We know there's a thrust coming from the engines, usually 2 of them. And of course, there must be a large drag associated with that aeroplane. So, what have we got here? Well, you can consider what's happening in 2 different directions here. One, we're going to look at what's happening vertically, and the other one, we're going to look at what's happening horizontally. So first of all, vertically, we have the weight minus the lift, or indeed we could rewrite those the other way around. The point being here is that vertically, the resultant force is 0. So which of these 2 situations do you think we're going to have? Do you think it's going to be stationary, or do you think it's going to be moving at a constant velocity in the vertical direction? And of course, the answer here is that it is stationary vertically. In the vertical direction, i.e. it doesn't move. What about horizontally now? We have the drag and the 2 thrusts. So let's talk about the drag. Let's go thrust first, minus the drag, and that gives us the resultant force horizontally, again being 0. So which of these 2 things is going to be stationary, or is it going to be a constant velocity in the horizontal direction? Of course, it's going to go as a constant velocity. In other words, you're cruising at a constant height. So we're cruising at a constant height and speed. And direction as well, should we say. Good. So there, as we have it, is Newton's first law. And I suppose actually I'll do one more example for you, just to make sense of this. And that is, what would happen if we had the Earth and the Moon and someone out in space drifting along? If they're drifting, well, first of all, we can say that we're very, very far away from either planet. So we can assume that the resultant force here is going to be 0. Or even indeed, right between the planets with respect to their size, there's going to be an equal pull. The resultant force is 0. And the point I want to make is that if you were stationary originally between those 2 planets, then you remain stationary. Whereas if you're moving, then you move at a constant velocity. So it doesn't matter where you, as long as there's no resultant force, if you're stationary, you stay stationary. If you're moving at a constant velocity, you stay moving at that constant velocity. Good. Okay, there's Newton's first law. So just remember, Newton's first law is about the absence of a resultant force. Okay, so we're going to move on to another page here, looking at Newton's second law. So, and this is probably the most famous one, or the easiest for people to recall. Essentially, it's the equation F equals ma, or F resultant equals ma. But let's take a few looks at what's happening here. It's like the first one was the absence of resultant force. This is what happens when there is a resultant force. So if there is a resultant force. And what does that do? Well, if there is a resultant force, then you simply have a change in speed. So there is a change in, velocity, of which that can be either speed or direction, or both. And the amount by which that changes, the rate of change, depends upon the mass of the object. Good. So highlights to this one are, so the important bits of this one are, if there is a resultant force, then you would get a change in velocity. And when we mean velocity, we mean speed or direction or both. That's the major part. So let's, I've just got to join those two together. There we go. So let's take a look at some examples. Now there's a famous one from GCSE which looks at how a skydiver behaves when he falls from an aeroplane. Let's actually take a look at that one. That's really useful. I'm going to look at that one first. So here is my skydiver. And then a little bit later on, it's got a rather big head. And then once more a bit later on. And then finally with parachute opened. Where are the forces? Well, in each case, there is weight associated with this person, and that does not change. But as they start to fall, and then they progressively fall faster and faster until they open the parachute, what will be happening is air resistance will be increasing. And then suddenly, huge air resistance. And I suppose there's space for one more, whereby the air resistance has significantly decreased. Okay. So what does this tell us? Well, in this first instance, there is a large resultant force downward, whereby we're taking away the downward force and the upward force, thereby leaving us a resultant force. In the second one, we have a large downward force again, an increasing upward force, so our resultant force is much smaller. And in the last one, of course, you take them away, leaving us with 0. So suddenly we've got a Newton 1 in this instance. We've definitely got Newton 2 in these instances. In other words, we've got a large change of speed. Or the acceleration is big. Here, the acceleration is smaller. Newton 1 suggests that there is now no resultant force in this instance. So what's going to happen? Well, they're not going to suddenly stop in the middle of the skies. They're going to fall at a constant velocity. So we have a constant velocity. Here, suddenly at the speed they're travelling at this velocity, with a parachute open, you have a huge air resistance compared to the weight. So therefore, we have weight minus air resistance, leaving us with quite a considerable upward force. So you de-accelerate. You don't just fly upwards. That means you're de-accelerating. So we have a Newton 2 here. And of course here we have another Newton 1, because as it de-accelerates, it reaches a point where the new speed, the air resistance, and the weight are identical. And therefore we have another constant velocity. A second terminal velocity, as it were. Okay, now, in GCSE, I hope you know from a velocity time graph that the gradient is equal to the acceleration. So in this first instance here, we have a large acceleration, so we're going to get a large gradient initially. Then the acceleration decreases, so therefore the gradient decreases. Of course, at a constant velocity, we're going to get zero gradient, because there is no acceleration. De-acceleration will be negative, and another constant velocity will be flat. And this is what the graph should look like, where we have one constant terminal velocity and another, or the second terminal velocity. Okay, so there's an example of how forces, so once again, that part is steep, then it's decreasing, then it flattens off to a constant velocity, massive deacceleration, and then levelling off again to another second terminal velocity. So if there is a resultant force, then there is a change in velocity. That's the important point here. Let's see what we can do in terms of a second example, because it says here, of course, there is a change in velocity, which means a change in speed, or indeed a change in direction. Let's look at the change in direction one. I'm going to try and draw a circle, a sphere. Okay, that's not bad. And around that, I'm going to draw a satellite that's going around the Earth. Now, these satellites rotate at a constant speed. And of course, if you say a constant speed, then people often think to themselves, right, it's going to be in Newton's first law. However, of course, you realise that this is constantly changing its direction. Though its speed remains constant, there is a change in direction. So if there's a change in direction, then Newton 2 is actually what's happening, because, look here, there's a change in direction, so therefore Newton's second law must come into effect. So therefore, this is not possible in Newton 1. But if there's a change in direction, then you might ask yourself, therefore, if there's a change in direction, there's a change in velocity, so therefore there must be a resultant force. Where is the resultant force in this case? Well, the resultant force is the force due to gravity, or indeed the weight. And that is always acting, and therefore changing its direction. So its new direction here will have new velocity. That's not a bad one. It has a velocity which is the same length, i.e. same speed, but it has a different direction. And here will be the same, there, and there, etc., etc. So you do have a constant speed, but there's a change in direction, so Newton's second law is in effect, and the resultant force is acting towards the centre. Okay, there's another one. And then, I suppose, the last one, which might actually be easier if I move these out of the way that way, because I've got some horizontal diagram coming along. What happens if we have a car on a road and we have three situations? I've got to draw three cars now, this is going to be problematic. There we go, another one, and a final one. Right, in the first instance, we hit the accelerator, or your parents do, depends if you drive, and so therefore, and that's the only force that's present, the engine driving it. There's a little bit of friction, but negligible amounts. The second one, however, picked up considerable speed, and the drag and the driving force are equal. And the third one, you take foot off the accelerator a little bit at that certain speed. So once again, what's happening in these situations? Well, there is very much a resultant force acting forward. So therefore, this is a Newton 2. The resultant force here is 0, so therefore this is very much Newton 1. And the resultant force here is actually that way, so this is a Newton 2. And maybe I should just draw this bit will be an arrow pointing in that direction. Okay, so what happens in the first instance? We get a huge acceleration. In the second one, we have so let me write that in, acceleration. In the second one, of course, their forces now are balanced, so it's Newton 1, so it doesn't suddenly stop. It moves at a constant velocity. And in the third one, of course, you have a much larger drag than you have driving force, so the resultant force is backwards, hence we have a deacceleration. And probably it's worth mentioning in this instance here, this final idea of F equals ma, because the acceleration that's here, of course, depends upon the mass of the car. If you have a light car, the acceleration is going to be bigger than if you had a heavy car. Okay, let me just group all those together. Excellent. Okay, moved it out of the way. Let's bring that back up into large again. So we just say, note again, that if the resultant force, you get a change in speed or direction. Here was a change in speed, in this instance. This one was a change in direction. Right. So where does that leave us? That leaves us with the last one, which is Newton's third law. Now this is one that people often get wrong. It's often quoted incorrectly. I'm going to try and clear that up for you. People often hear it as there are equal and opposite forces. Which isn't wrong, but the real problem that people have is that they often don't realise that these forces must act on different bodies. So let me give you an example. If we had, all right, a nice easy example would be something like two ice skaters on the ice, and they have pushed off each other. And if they have pushed off each other, then they are going to move in opposite directions from each other. Because this person, in pushing on this body here, has of course created a force on them backwards, as well as creating a force on them. So we have an equal force, which is in opposite directions, but it's on different bodies. So therefore the result is, for the brief moment, you will have the force which causes this body to move that direction and that body to move in that direction. And because it's on ice, it's instantly turned to a Newton 1, where they just start to drift apart from each other. The important point here is that it must be on the different bodies. So there's an easy example. Now we start turning to something a little bit more complicated. What happens if we have somebody standing on the floor? There is a weight associated to them. And where would this equal and opposite force be? Because if we have a force present, there needs to be another force as well. And often people say, well, that's the upthrust. Because it does satisfy the criteria. It's equal in amount. That's why the person's stationary. It's in an opposite direction, of course. That's why it's stationary. Its resultant force is 0. It's on a different body. And so therefore there's our equal and opposite force. And the last point you need to state is that it must be of the same type of force. So if this is a weight, then the equal and opposite force must be a weight type or gravity force as well, and those are definitely not gravity forces. In actual fact, what's happening is, if this is the Earth, there is a pull, because you're being pulled towards the centre of the Earth, you indeed are pulling the centre of the Earth up to you with the same amount of force, because here it is the same type of force that's important. It's on different bodies, it's equal in quantity, and it's in an opposite direction. So that is our Newton 3 pairing. You might ask yourself, well, what on earth is the other force to this upthrust here? Well, that is the compression which you're pushing on the ground. The ground therefore pushes up with the same upthrust. You're compressing the ground, you're sort of squeezing the grass if you're standing on grass, and therefore it's pushing back at you like a spring. You're compressing a spring. Okay, you can get caught in a little net if you're convinced of this. If you are still convinced that this weight and those upthrusts are equal and opposite forces, then what happens when you jump off a tower block and you're falling? There's still a weight associated with you, but suddenly this upthrust has disappeared. There's no upthrust. So you can't switch this law on and off. So where on earth is the other Newton 3? Where is the Newton's third law pairing? Some people then say, oh, that's easy because it's the air resistance creates the Newton's third law. And then I could say, okay, well, let's put this on the moon. And if it's on the moon, you can't suddenly switch off the Newton 3 pairing, but definitely the air resistance wouldn't exist. So now where's your Newton 3 pairing? And only then are you properly convinced that you're pulling the moon up with the same amount as the moon is pulling you down with. A Newton 3 pairing. So, important here, very important in actual fact, is that they are equal. They are opposite, they're on different bodies under the same type of force present. Trying to think of another example of where that would be. I think you're only likely to get into trouble when you're trying to describe weights because of this tweak with the gravity. Most things are going to be about forces on different bodies. So therefore, if we had, for instance, a cannonball and an explosion takes place in the cannon, of course, thereby thrusting the cannonball out, the force exerted on the cannonball is identical to the force exerted on the cannon. It's equal in size, hence these arrows are the same size. It's in an opposite direction. It's on a different body, because one's on the cannonball, the other's on the cannon. And the interesting part here is we not only have a Newton 3, but the Newton 2 dictates how much acceleration the cannonball has compared to the cannon. And of course, if you take that mass, take that force and divide it by the very big mass, you get a small acceleration for the cannon. Whereas if you take the same force and divide it by a little mass of the cannonball, you get a large acceleration of the ball. Good. Does Newton 1 come into it? Probably not, because there's always friction involved. That's probably worth saying, actually. Newton 1. Friction often prevents this. Good. Okay, what else would there be? Let me give you one more example if I can. It's oh, that's a bit of a shame. That one's come apart. Let's look at one more example where you have a space station and somebody pushes off one side of the space station. Oh, that's right, space station. Somebody pushes the space off at one side of the space station and causes not only the space station to move, but for them to move. Of course, it's an equal force, but the acceleration is very small on the space station and considerably larger on the person, just like the cannonball situation happening here. The person then moves backwards and will eventually collide with the other side of the space station and cause it to stop completely. And that's because the identical forces will relate at this end, which cancel out. So you can make a space station vibrate a little, but this is no means of propulsion. Right, now, let's talk about how Newton and momentum come into play. Okay, Newton's first law. I suppose you could say in the absence, if the resultant force is zero, or you could say if the, and I hope you realise that momentum is given the symbol P, if the momentum is zero, then the same happens. So that's easy enough to consider. Newton 2, however, rather than saying F equals ma, Newton started by saying that the force is equal to the rate of change of momentum with time. So that is the rate of change momentum. So in other words, if there is a force present, then it changes the momentum. And I suppose, now let me just write in the MV so you can see what momentum is. I'm sure you recall that. Let's see how these two link. Well, of course, F equals the rate of change of momentum with regards to time, which is same as saying the change in momentum divided by the time period, which is mass, change in velocity divided by the time period, which is indeed mass times the acceleration. So you can see here how this term turns to acceleration, which links back to the first one, which makes good sense. And finally, Newton 3. Oops, let's get this in there. Rather than just saying that the force exerted is going to be equal and opposite, it's basically saying the same about momentum. Rather than, actually, I'm not going to write that down in that form. Let me describe this better with that space station example. The space station example said that momentum, when objects interact, the momentum given to one is equal to the momentum given to the other. Actually, it's probably easier to describe in this way, because when you're talking about forces, then you have to divide by the masses to give you accelerations. And therefore, it's a little counterintuitive. The cannonball moves faster than the cannon. Whereas when you're dealing with momentum, of course, it's identical. The momentum on one is equal to the momentum on the other. And so therefore, when I gave that second example of the person striking this side, those of momentum cancel, and so therefore the space station stops. So I think often it's easier to consider Newton's third law as in terms of momentum rather than in terms of force. Okay, hope that all made sense.